Welcome back to AI Podcasters, and you know what that means. It's time for another deep dive.
Right.
Today, we're shrinking down,
Shrinking down.
to the subatomic level
Right.
to explore the fascinating world of atoms, the
Yes.
building blocks of, well, everything.
That's right. Whether you're prepping for a chemistry exam or just curious about what makes up the universe,
Yeah,
understanding atoms is like getting a glimpse into the fundamental code of reality.
I love that the code of reality.
No.
Okay, so for those who might need a little refresher, let's start with the basics.
Okay.
What exactly is an atom?
In the simplest terms, an atom is the smallest unit of an element that still retains the properties of that element.
Okay.
For example, a gold atom is the smallest possible piece of gold you can have. Any smaller, and you've broken it down into its subatomic components, which don't behave like gold anymore.
So it's like a Lego brick.
Yes.
You can build all kinds of amazing things with it, but if you break it down further, it's no longer a functional Lego piece.
Exactly. And just like Legos come in different shapes and sizes, atoms have their own internal structure. A common analogy used to visualize this is comparing an atom to a tiny solar system.
Okay, I've heard that one before. The nucleus is like the sun at the center,
Right.
and the electrons are like planets orbiting around it, right?
That's the basic idea, though. It's a bit of an oversimplification, as we'll discuss later when we get into quantum mechanics.
Okay.
But for now, it's a helpful visual.
So if we zoom into the sun or nucleus of this tiny solar system, what's going on in there?
The nucleus is incredibly dense and packs a positive charge. It's composed of two types of subatomic particles, protons and neutrons.
Right, I remember those from high school science class.
Mm-hmm.
Protons are positively charged and neutrons have no charge. They're neutral.
Yes.
But what exactly are they doing in there?
Well, each element is defined by its number of protons, known as its atomic number.
Uh-huh.
It's like the element's fingerprint.
Okay.
For instance, hydrogen has 1 proton, helium has 2, and so on. So those protons in the nucleus are essentially determining what kind of atom it is.
So if you could magically add a proton to a carbon atom's nucleus,
Uh-huh.
you'd transform it into nitrogen. That's pretty wild.
Precisely. The number of protons is what dictates the element's identity.
Okay, that makes sense. Now, what about the neutrons?
Okay.
They don't have a charge.
Right?
So it seems like they're just chilling in the nucleus.
Mhm.
What's their purpose?
Neutrons are crucial for the stability of the nucleus. Remember, protons are all positively charged, so they naturally repel each other. If you had a bunch of protons crammed together without any neutrons, they'd fly apart due to electrostatic repulsion.
Oh, so the neutrons act like a kind of a buffer,
Yes,
keeping the protons from repelling each other too strongly.
that's a great way to think about it. Neutrons help to moderate the strong repulsive forces between the protons, ensuring the nucleus remains intact.
It's like they're the peacekeepers in a crowded room,
Yeah,
making sure things don't get out of hand.
a very apt analogy. Now let's step away from the bustling nucleus and talk about those tiny particles whizzing around it. The electrons.
Ah, yes. The electrons, I've always pictured them like tiny planets orbiting the sun-like nucleus.
Right.
But something tells me it's not quite that simple.
You're right. The planetary model is a useful starting point,
Yeah.
but it doesn't fully capture the true nature of electrons.
Okay.
Quantum mechanics tells us that electrons behave more like waves than particles, and that they don't follow neat, predictable paths.
Okay. I'm intrigued. So if they're not orbiting like planets, what are they doing?
Instead of fixed orbits, electrons exist in regions of space called orbitals.
Okay.
Imagine these orbitals as fuzzy clouds where electrons are most likely to be found.
Uh-huh.
We can't pinpoint their exact location at any given time, but we can calculate the probability of finding them in certain regions.
So it's more about probability than a fixed trajectory.
Yes.
That's a pretty radical departure from the planetary model.
It is. This concept of electron probability is one of the cornerstones of quantum mechanics,
Okay.
and it has some pretty mind-blowing implications for how atoms behave.
I'm starting to see why quantum mechanics has a reputation for being mind-bending.
Yeah.
But before we dive too deep into that rabbit hole,
Sure.
can we back up a bit and talk about what these electrons do?
Okay.
They must have a purpose beyond just existing in these fuzzy clouds, right?
You bet they do. Electrons are the key players in chemical bonding,
Okay.
the process by which atoms join together to form molecules.
Okay.
The way electrons are arranged in an atom determines how it will interact with other atoms and what types of bonds it can form.
So that's where we start to see how atoms become the building blocks of matter, right? They
Yes.
link up with each other through these electron interactions.
Precisely.
Mhm.
And those bonds are what give different molecules their unique properties.
Yep.
But before we delve into the different types of bonds, let's take a closer look at how electrons are organized within an atom. You mentioned energy levels earlier, and that's a crucial piece of the puzzle.
Right. I vaguely remember something about energy levels from chemistry class.
Mm-hmm.
It's like electrons have their own designated floors in an atomic apartment building.
Right. That's another great analogy. Each electron in an atom occupies a specific energy level,
Okay.
and these levels are quantized,
Yeah.
meaning electrons can only exist at specific discrete energy levels, not in between.
So an electron can't just hang out wherever it wants. It has to be on a specific energy level.
Exactly. Think of it like climbing a ladder. You can only stand on the rungs, not in between them. Electrons can jump to higher energy levels by absorbing energy.
Right?
And when they drop back down to a lower level, they release energy often in the form of light.
Wait, so all those dazzling colors we see in fireworks and neon lights
Mm-hmm.
are actually caused by electrons jumping between energy levels.
That's right. It's all thanks to these tiny particles and their remarkable quantum behavior.
What?
But we're getting ahead of ourselves.
Okay.
Let's wrap up part one by revisiting those floors in the atomic apartment building.
Okay. I'm ready to learn more about these energy levels and how they impact an atom's behavior.
Hmm.
But we'll have to save that for part 2.
Indeed, we have much more ground to cover in our deep dive into the atom. Stay tuned. Welcome back to our atomic exploration. We left off talking about how electrons are organized into different energy levels within an atom. It's a bit like those nested Russian dolls. There's always another layer to uncover.
Exactly. We were just about to dive into those energy levels you were describing. It's like each electron has an assigned floor in the atomic apartment building, but there are rules about how they can move between floors.
That's a great way to visualize it. These floors are officially called electron shells, and each shell can hold a certain number of electrons. The innermost shell closest to the nucleus can hold up to 2 electrons. The next shell can hold up to 8, and so on.
So it's not like a free-for-all where electrons can just zoom around wherever they want.
Mm-hmm.
There's a specific order to things.
Absolutely. Electrons fill up the shells in a very specific way, starting with the lowest energy levels closest to the nucleus and moving outwards. Think of it like filling up seats in a theater. You start with the best seats down front.
Okay, that makes sense. But why are these energy levels so important? What difference does it make which shell an electron occupies?
Well, the energy level of an electron determines its potential energy, which is its stored energy due to its position. Electrons in higher shells have more potential energy than those in lower shells, just like someone standing on a higher floor of a building has more potential energy than someone on the ground floor.
So the higher the energy level, the more excited the electron is, so to speak.
Exactly. And these excited electrons play a crucial role in chemical reactions. When an atom absorbs energy, its electrons can jump to higher energy levels. And when those excited electrons drop back down to lower levels, they release energy often in the form of light or heat.
So that's how we get things like the vibrant colors and fireworks and neon signs. It's all about electrons transitioning between energy levels.
Precisely. Those dazzling displays are essentially visual representations of electrons losing energy and emitting photons of light.
Wow, that's pretty amazing.
Uh,
So these electron transitions are responsible for a lot of the phenomena we observe in the world around us.
Absolutely. And speaking of interesting phenomena, let's revisit a topic we touched upon earlier, isotopes.
Yes, isotopes. Those are atoms of the same element with a different number of neutrons, right? Like siblings with slightly different personalities.
Precisely. Isotopes have the same number of protons, which defines the element, but they have varying numbers of neutrons. This means they have the same atomic number, but different mass numbers.
Right. The mass number reflects the total number of protons and neutrons in the nucleus.
Mm-hmm.
So an isotope with more neutrons will be heavier than one with fewer neutrons, even though they're both the same element.
Exactly. And while isotopes of the same element share most of their chemical properties, their differing masses can lead to subtle but important variations in their physical behavior.
Can you give us an example of how these subtle differences play out in the real world?
Certainly. One fascinating example is carbon dating. You know how archaeologists can determine the age of ancient artifacts? That's thanks to carbon-14, a radioactive isotope of carbon.
Wait, radioactive? You're telling me some atoms are naturally radioactive?
That's right. Some isotopes are unstable, meaning their nuclei have a tendency to decay over time, releasing particles or energy in the process. This is what we call radioactivity.
So those extra neutrons in some isotopes can make them a bit unpredictable, huh?
In a way, yes, carbon-14 is a naturally occurring radioactive isotope that decays at a known rate. By measuring the amount of carbon-14 remaining in an organic sample, scientists can estimate how long ago the organism lived.
Wow, that's incredible.
Yeah.
So isotopes are not only fundamental to understanding the structure of matter, but they also have incredible applications in fields like archaeology and medicine.
Absolutely. And speaking of applications, let's not forget the importance of understanding atomic number and mass number in chemistry.
Right, we defined those terms earlier, but can you remind us why they're so important?
Certainly. The atomic number, as we mentioned, is the number of protons in an atom's nucleus. It's like the atom's ID card telling us which element it is, and the mass number is the combined number of protons and neutrons. Together, these two numbers give us a complete picture of an atom's composition.
It's like having both a name and a weight class for each atom.
Precisely. Knowing both the atomic number and mass number allows us to identify specific isotopes and understand their properties. And as we've seen, isotopes can have vastly different behaviors depending on their neutron count.
Okay, so we've got protons defining the element, neutrons affecting stability, and isotopes and electrons whizzing around in these quantized energy levels, sometimes jumping between them and releasing energy. It's a lot to keep track of.
It is indeed a complex and fascinating world down at the atomic level,
Mhm.
but we've only just scratched the surface. There's so much more to explore, from the different types of chemical bonds to the mind-boggling world of quantum mechanics.
I'm definitely feeling a bit overwhelmed, but in a good way.
Yeah.
It's incredible to think about all this complexity happening at a scale we can't even see.
And yet it's this intricate dance of particles and forces that ultimately gives rise to everything we know and experience in the macroscopic world. But let's save those deeper explorations for part 3 of our deep dive.
I'm on the edge of my seat already. We'll be back soon to delve into those deeper mysteries of the atom. Welcome back to the final part of our atomic adventure. We've journeyed from the nucleus to the electron cloud, explored energy levels and isotopes, and even dipped our toes into the strange waters of quantum mechanics.
It's been quite a ride through the subatomic world, but now I think it's time to zoom back out and see how all this tiny scale activity translates into the stuff we see and interact with every day.
Exactly. We've been talking about atoms as the building blocks of matter, but I'm curious to understand how those blocks actually fit together to create the incredible diversity of materials we see in the world around us.
Well, that's where the magic of chemical bonding comes in. Atoms are social creatures. They rarely exist in isolation. Instead, they tend to join forces with other atoms to form molecules, and it's the types of bonds they form that determine the properties of those molecules.
Okay, so we've got these atoms with their protons, neutrons, and electrons all configured in specific ways. How do they actually link up with each other?
There are several types of chemical bonds, but two of the most common are covalent bonds and ionic bonds.
I remember those terms. We touched on them briefly in part 1, but I'm ready for a deeper dive. Let's start with covalent bonds. How do those work?
In a covalent bond, atoms decide to share electrons. It's a bit like a friendly agreement where each atom contributes one or more electrons to a shared pool, and those shared electrons help to fill the outer electron shells of both atoms involved.
So it's like they're pooling their resources to achieve a more stable arrangement.
Exactly. Atoms are always striving for stability, and having a full outer electron shell is a key part of that stability. So by sharing electrons, they can achieve that desired full shell.
Can you give us a real-world example of a molecule formed through covalent bonding?
Absolutely. Water is a classic example. A water molecule, H-arrow, consists of two hydrogen atoms covalently bonded to an oxygen atom. Each hydrogen atom shares its one electron with the oxygen, which in turn shares two of its electrons. This sharing creates a stable configuration where all three atoms effectively have full outer shells.
So that simple act of electron sharing is what gives water its unique properties.
In a nutshell, yes. Those shared electrons and the specific way they're arranged are responsible for many of water's remarkable properties, such as its high boiling point, its ability to dissolve many substances, and even its role as a key ingredient for life.
That's incredible. It's mind-boggling to think that such tiny interactions between atoms can have such profound impacts on the macroscopic world.
Indeed it is. Now let's move on to ionic bonds. These are a bit different from covalent bonds. Instead of sharing electrons, atoms involved in an ionic bond completely transfer electrons from one to another.
So it's more of a give and take situation rather than a sharing arrangement.
Precisely. When an atom loses an electron, it becomes positively charged, forming what we call a canary cation. And when an atom gains an electron, it becomes negatively charged, forming an anion.
Okay, so we've got these oppositely charged ions. What happens next?
Well, just like magnets attract each other, these oppositely charged ions experience a strong electrostatic attraction. This attraction is what forms the ionic bond.
Can you give us an example of a compound formed through ionic bonding?
Certainly, table salt or sodium chloride, NaCl, is a classic example. A sodium atom readily donates its outermost electron to a chlorine atom. This creates a positively charged sodium ion, Na+, and a negatively charged chloride ion, Cl. The electrostatic attraction between these ions forms the ionic bond that holds the salt crystal together.
So the reason salt dissolves in water has something to do with these charged ions interacting with water molecules.
That's right. The polar nature of water molecules allows them to surround and separate the individual ions, effectively dissolving the salt crystal.
This is fascinating. It's amazing to see how these atomic interactions, whether through sharing or transferring electrons, create the vast array of materials that make up our world.
And we've only just scratched the surface of the fascinating world of materials science. But before we get too carried away, I think it's time to revisit something you mentioned earlier, that feeling of being overwhelmed, but in a good way.
Yes, it's almost a bit dizzying to contemplate the sheer complexity happening at the atomic level, but it's also incredibly awe-inspiring to realize that everything we see and touch, from the simplest substances to the most complex life forms, is ultimately built from these tiny interacting particles.
It's a humbling realization, isn't it? The entire universe, in all its vastness and diversity, is essentially a magnificent symphony of atoms, all following the same fundamental laws of physics and chemistry.
It makes you wonder what other mysteries and wonders are still hidden within those tiny building blocks.
Indeed, the journey of scientific discovery is never-ending. And who knows what groundbreaking insights await us as we continue to explore the atom and its infinite possibilities.
Well, on that note, I think we've reached the end of our atomic deep dive. It's been an incredible journey, and I feel like I've gained a whole new appreciation for the amazing world that exists at the subatomic level.
I'm glad to hear that. And remember, the key to unlocking the universe's secrets lies in curiosity and a willingness to keep asking questions, no matter how small or seemingly insignificant.
Thanks for joining us on this atomic adventure. Until next time, keep exploring, keep learning, and keep diving deep into the wonders of the world around us.